yesterday about hybridization explained, and based on hybridization, today I will discuss about geometry or the structure and shape of the molecule on the basis of hybridization. For neutral molecule or species, either cation or anion, here if we can identify the number of hybrid orbitals. HO means hybrid orbitals. Here number of hybrid orbitals 1, there is no intermixing. Your number of hybrid orbitals are 2, that is one is S and one is P. That's why its hybridization is SP. Here there is no hybridization. Number of hybrid orbitals are 3, one is S, 2 are the P, then its hybridization is sp2. Number of hybrid orbitals are 4. Among 4, 1s, 3p orbitals. Then sp3 are also here 1s, 2p, and 1d is present, that is dsp2, and so on. So based on number of hybrid orbitals, we can easily estimate its hybridization. Okay. So we know the hybridization. On the basis of hybridization, geometries are there. If it is sp, that is a linear shape. If it is sp2, T-planar, trigonal planar structure. It is tetrahedral structure. It is a square planar structure. If it is sp3d is there, that is your bipyramidal structure, that is trigonal bipyramidal structure. If it is sp3d2 or d2sp3 is there, that is octahedral structure. Here sp3d3 is there, pentagonal bipyramidal structure takes place. So here on the basis of this hybrid orbitals sp, sp2, sp3, d2, sp2, sp3d, sp3d2. Here easy to design its shape or the geometry of the molecule. So here there is a little bit confusion and a number of questions arises for students, always confusion. To identify the exact geometry of the molecule, we want compulsory the concept of Vesper theory, valence shell electron pair repulsion theory, as well as hybridization theory, because on the basis of lone pair concept, Vesper theory, valence shell electron pair repulsion theory, due to the presence of lone pair and lone pair, bond pair, and bond pair, its geometry changes from regular to the irregular order. So to get the clarity about geometry, compulsory we want the concept of Vesper theory phosphates as well as hybridization. Simply for any molecule to find out the hybridization, these are the two important formulas. Better you remember this formula for all, either for neutral molecule or the species. For any species or any molecule, we know the V value, M value, and C and A values. By substituting these, we can easy to calculate the hybrid orbitals. number of hybrid orbitals. On the basis of hybridization, we know the number of hybrid orbitals, then hybridization is to get it. Then geometry also easy to get it. Here V is number of valency electrons. Number of valency electrons of central element. Central element it is. Now here M is number of only monovalent. Valency is 1. Number of only monovalent atoms. And here the C is the charge on cation. Charge on cation. Here A is charge on anion. So we know this concept, then easy to find out. I'll take 3-4 examples. One is for neutral molecule, another one is cation, another one is anion. Hybridization easy to find out. See here, I'll take one best example is CH4 molecule. So generally, central atom of an element is generally less electronegativity element we can take, or element which is bonded with more number of other elements. Once we can observe here the CH4 in these, around carbon 4 hydrogen atoms are bonded. Less electronegativity is here hydrogen, but carbon is considered as the central atom of element because only one which is bonded with more number of other different elements. That's why it is considered as a central atom of an element. It is a neutral molecule because some of their oxidation state must be equal to 0. Neutral, there is no charge. It is not a cation, it is not an anion. It is a neutral molecule. For this neutral molecule, central atom of element is C, central element. Central element is C. Its valency is equals to 4. Number of valency electrons, combining capacity. Valency electrons. Around this carbon monovalented means hydrogen is a monovalented. Your 17th group elements valency combining capacity also 1 monovalented. Alkali metals are the monovalented. Such a monovalented. Oxygen is a divalent. Nitrogen is a trivalent. So here monovalented M value. Monovalented atoms M is equals to here 4. Yeah, the C is equals to charge on anion 0, charge on cation also 0. We know number of hybrid orbital formula 1 by 2 into 4 plus 4 minus 0 plus 0. That is equals to 8 by 2, that is 4. So the number of hybrid orbitals are 4. Now 4 means they are generally one s orbital and remaining 3 are the p orbital. It is a sp3 hybridization. Geometry is without a lone pair. If it is a sp3, its geometry is tetrahedral. If it contain one lone pair at least, based on hybridization and based on Vesper theory, we can decide its geometry. Based on hybridization and Vesper theory, I will compare with the 2 examples, ammonia and methane molecule. Now, among these 4, one is s orbital, remaining 3 are the p orbital. So, here the sp3 hybridization. If it is sp3, geometry is tetrahedral geometry. Clear. I'll take one ion species, very simple species. For that, I'll take NH4 plus. It is a positively charged ion because on NH4 plus, that plus is on hydrogen ion. It forms a coordinate covalent bond. That coordinate covalent bond also considered as a covalent bond. I'll explain after this coordinate covalent bond. Now here central atom of element is nitrogen. For this details, valency number of valency electrons are 5, monovalented are 4. Your charge on cation is 1, anion there is no negative charge. Your plus 1 is there, 1, 0. So by applying this formula, your hybrid orbitals is equals to 1 by 2 into V plus M minus C plus A. Now it is 1 by 2 into 5 plus 4 minus 1 minus or plus minus 1 plus 0. Now that is 8 by 2, that is 4 sp3. It is also a tetrahedral shape. Yeah, there is no any lone pairs on nitrogen atom. It is a cation species. Its geometry is tetrahedral without any lone pairs. Then I'll take one more example, that is for anion. I'll create one anion. I will take hybridization. What type of hybridized orbitals are involved in a given species? So many examples given previous year, previous NEET examination. So it is SO3 minus 2. Third example, central atom of an element is in this case a less electronegative element, carbon. Yeah, the carbon valency details number of valence electrons are 4. Your monovalented are here 0 because oxygen is a divalent. Charge on cation is 0, but anion is minus 2 charge. Now formula we know, here minus 2 or plus 2, let it its charge, only take the charge, only 2. Already here in this formula minus and plus created. Now for this hybrid orbitals is equals to 1 by 2 into 4 plus 0 minus 0 plus 2, that is 6 by 2, that is 3, means 1s and 2p orbital. The hybridization of carbon in carbonate ion is sp2. It is a T-planar, trigonal planar, means it is a carbon. Around carbon your 4 electrons are there. One is like double bond. This is the O minus and this is the O minus. Yeah, the number of sigma bonds are 3. Pi bonds are not involved in hybridization. That's why your 3 sigma bonds are there. By using these number of hybrid orbitals, total number of bond pairs and lone pairs also we can design it. Now here the bond pairs means 3, lone pairs means for that 0, total 3. Its hybridization is sp2. Now its geometry is trigonal planar, triangular planar geometry. So in this manner, for any example, we can easily estimate its hybridization by using these 2 important formula, by using VB theory, by using Vesper theory, by using hybridization. Easy to estimate its hybridization geometry, bond angle, bond lengths. So many examples given in a previous year NEET, JEE and KCET. Which of the following pair isostructural? Number of questions created based on this. Okay. Now with the help of all this, I'll give a simple example. I'll introduce Vesper theory, hybridization. Both are see here I'll take CH4 molecule and NH3 molecule and also water molecule. On the basis of VB theory, the central atom of element is carbon. Around carbon atom 4 hydrogens are bonded, which are tetrahedrally bonded. Your number of sigma bonds are 4 are there. Bond pairs BP are 4. LP or 0 neutral molecule, we can use 4 plus 0 equal to 4. So its geometry, sorry, its hybridization is sp3. Similarly, here around the nitrogen atom, 5 valence electrons are there out of 5. One pair is remains present as lone. This is LP, that is non-bonded electron pair. This is electron pair. Now 3 are the bonded like this: iodosine, iodosine, iodosine. Sigma bonds are like, your bond pairs are 3 and LP lone pairs are 1. Your total or hybrid orbitals are your 3 plus 1 equal to 4. Its hybridization is sp3. Then here oxygen is the central atom of element. 6 valence electrons are there. Out of 6, here the 2 are the paired like this. Then 2 are the bond pairs, sigma bonds bond pair, and these 2 are the LP lone pair. So the bond pairs are 2 and LP are 2. Hybrid orbitals are 2 plus 2, 4. 4 means sp3 hybridization. So on the basis of these 3, we can introduce both the Westphal theory as well as hybridization. According to hybridization concept, if the central atom of an element undergoes sp3, its geometry, shape of the molecule is tetrahedral. Tetrahedral. Here also sp3 is there, geometry is tetrahedral. Tetrahedral shape. Here also its geometry is tetrahedral shape. So on the basis of hybridization concept, in all the 3 cases, 3 examples, central atom of an element undergoes sp3. So its geometry is tetrahedral, tetrahedral, tetrahedral. But here after hybridization, valential electron pair repulsion theory introduced by 4 people already as explained. Due to the presence of some pair of electrons, lone pairs and bond pairs, here we know LP and LP electron repulsions are more. These are the repulsions order. Repulsions order, it is order of repulsions. Then LP and BP, then BP and BP. So are the LP electron pair, lone pair electron pair repulsions are more than compared to lone pairs and bond pairs, than compared to bond pairs and bond pairs. In this case, all the 4 are the bonds only. That's why here bond pair and bond pair repulsions only present here. That's why such a bond pair repulsions are maximum minimized and arranged normally tetrahedral. It is a regular shape. It is regular shape according to hybridization. The shape is tetrahedral if it undergoes sp3 hybridization. But in this case, ammonia, the central atom of an element undergoes sp3, but its geometry is not tetrahedral. Its geometry is pyramidal geometry. Pyramidal, that is due to lone pair and bond pair repulsions. Lone pair and bond pair repulsions, and also present here a bond pair and bond pair. This the lone pair and bond pair repulsions are there. That's why the regular geometry, this is the regular geometry changed to irregular shape. Irregular shape, that is due to the presence of lone pair and bond pair repulsions. That is a pyramidal structure. That's why to explain the geometry of the molecule, perfectly to explain the geometry of the molecule, we want the concepts of Westphal theory as well as hybridization concepts. Without knowing hybridization and without knowing Westphal theory, without knowing VB theory, difficult to estimate exact geometry and its biodata, number of lone pairs and bond pairs. That's why finally, if you know the exact story about a central atom of an element, that is in which group, valency is how much, how many electrons are participated in a chemical bond, how many lone pairs are there, how many bond pairs are there, and on the basis of lone pairs and bond pairs, is it neutral molecule or any species, or due to the occurrence of lone pairs, what happens? Its geometry. On the basis of all these points, we'll get accurate geometry. That's why for students in each and every one commutative and regular examination, to identify the geometry of the molecules are more difficult. To avoid that confusions, to estimate, to identify the accurate exact shape of the molecule, better you read thoroughly all synopsis or the postulates of Vesper theory as well as hybridization concepts. Here in this water molecule also, there are two lone pairs are there. Central atom of element undergo sp3 hybridization, but its geometry is not tetrahedral. Regular tetrahedral changes to another irregular order, that is a bent shape or V shape. Bent or the V shape. Now here tetrahedral changes to a bent like it is an irregular shape. That is due to the presence of more LP and LP repulsions are more than compared to the lone pair repulsions are more than compared to the lone pair and bond pair repulsions. These are very simple molecules, simple examples. In examination, they'll create a variety of different examples with the help of periodic table, number of elements given in periodic table on the basis of groups and periods. They'll create so many examples. We are ready to face, we are ready to answer the correct structure and geometry. Maximum number of questions are on the basis of which of the following pair is isostructural or isoelectronic species. For example, here boron trifluoride, there you go, boron trifluorides, and here NF3 nitrogen tetrafluorides. Among these, the central atom of element undergoes so what type of hybridization, and both are shows the same geometry or not. So like they'll create a variety of questions on the basis of hybridization concept. Here your central atom of an element is boron. Boron atomic number is 5. Number of valence electrons are 3. So our hybrid orbitals are 1 by 2 into 3 plus monovalented are 3. 0 plus 0, that is 6 by 2. Hybrid orbitals are 3. 3 means that is sp2 hybridization. So the central atom of an element, boron undergoes sp2. Now in this case, hybrid orbitals are 1 by 2 into valence electrons are 5 plus monovalented are 3. 0 plus 0, that is 8 by 2, that is 4. 4 means it is a sp3. So according to that concept, by seeing the formula, if it is sp3, we know sp3 means it is a tetrahedral according to the hybridization concepts. But yeah, its geometry is not a tetrahedral. This is wrong. Due to the presence of one lone pair, this is nitrogen, one lone pair is present, and here fluorine, fluorine, and fluorine. Even it undergoes sp3 hybridization, its geometry is pyramidal structure because here lone pair and bond pair repulsions are takes place. That's why just like a water molecule, its geometry is not a tetrahedral. From regular to irregular, geometry changes from tetrahedral to a bent-like structure. Like here also, regular is tetrahedral, changes to irregular, that is pyramidal structure due to the presence of lone pair and bond pair. This is AB3E type model. This is AB2 and E2 type model. Already explained. because on oxygen atom 2 lone pairs are there. That's why electron pair 2 are there. These 2 are the bonded atom. This is central atom of an element. This is AB type, AB4 type model without any lone pairs. That's why complete idea required about Whisper theory as well as hybridization, number of lone pairs and bond pairs, which is the central atom of element. Around the central metal of atom, what type of elements are bonded? To estimate the geometry, sigma bonds only participate involved. Pi bonds do not decide the geometry of the molecule. Clear? Now in boron trifluoride, your job sp2 hybridization means it is a trigonal planar structure. Your around boron 3 fluorine atoms are bonded like this. Yeah, there is no lone pair, regular geometry. According to Whisper theory as well as hybridization concept, geometry is same, trigonal planar structure. Like the right examples will create on the basis of hybridization. Better you concentrate all the examples and read thoroughly correlated with hybridization with Whisper theory. Then only we can easily answer the hybridization geometry of the molecule. Lone pair concept also important. Lone pairs and bond pairs concept also important. See, we are in a second year PCl5 structure is there. And your SF4 structure is there. So by using these two, central atom of element phosphorus, around phosphorus, 5 valence electrons are bonded. These 5 valence electrons are bonded with 5 same chlorine atoms. They are chlorine, 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 and chlorine. Sigma bonds or 5 sigma bonds are there here. By using number of bond pairs, direct bond pairs are 5 are there. They are the hybrid orbitals. That's why it's hybridization sp3 dehybridization. Here there is no lone pairs around phosphorus and PCl5 molecule. Only bond pairs only present. Regular order is exists. According to hybridization, if the central atom of element in a molecule undergoes sp3d, its geometry is trigonal bipyramidal structure. Bipyramidal structure is there. Here two important angles are there. Here 120 degrees and 90 degrees angles are there. Equatorial, axial. This is the axial and these are the equatorial angles, 120 and 90 degrees. Whereas in this case, around sulfur, 6 valence electrons are there. Out of 6, here the 4 are bonded with 4 fluorine atoms. 1 lone pair is present here. Total 6 valence. So according to the hybridized orbital concept, sigma bonds are 4 are there. And here 1 LP is there, a lone pair. 1 plus 4, 5. 5 hybrid orbitals means it is also a sp3d. Here also sp3d. In both the cases, central atom of an element undergoes same hybridization, but geometry is not the same. Varies, differs. Because in this phosphorus pentachloride, around phosphorus only 5 chlorine atoms without any lone pair. There is no such a repulsive forces. Only bond pair and bond to pair repulsions are very, very weak, less. That's why a regular shape, hybridization shape, that is sp3d, play bipyramidal structure, trigonal bipyramidal structure. But whereas in SF4, sulfur tetrafluoride, central atom of an element, sulfur contain 1 lone pair. Due to the presence of lone pair and bond pair repulsions, LP and BP repulsions, there is a somewhat more repulsive force than compared to, in this case, its geometry changes from regular to a irregular order. That regular order is originally T bipyramidal structure. Pyramidal structure, but it is not a pyramidal. Its structure is seesaw structure. Very, very important. That's why to estimate any one molecule geometry, compulsory we want a hybridization concept as well as Vesper theory, lone pairs, bond pairs concepts. Based on their lone pairs and bond pairs, here it's geometry, bond angles, bond lengths changes. So on the basis of all these points, three theories, VB theory, Vesper theory, and hybridization clearly explained geometry, bond angles, and bond lengths of the molecules, chemical molecules. Clear? So I'll explain that neat material. Tomorrow I'll cover the neat material. Better take one Xerox from WhatsApp and keep on side. And I'll solve the tomorrow maximum number of questions on the basis of these structures, isostructural, isoelectronic, and so on. Last 1 or 2 important concepts are there. Today maximum will cover the 1 or 2 important concepts. Tomorrow we'll discuss about neat previous questions. All previous year questions we'll discuss tomorrow. So after valency bond theory, valential electron pair repulsion theory, and hybridization, about covalent character, covalent bonds, geometry, bond parameters, dipole moments, polar and non-polar, polar molecule characteristics, ionic molecule characteristics, clearly explained. Then after that, covalent nature and ionic nature. After all these important theories, another important force, another important bond, that is a coordinate covalent bond. That coordinate covalent bond also called a day-2 bond. Here coordinates, coordinate covalent bond. That coordinate covalent bond also called day-2 bond. This day-2 bond or coordinate covalent bond is generally denoted by an arrow. That arrow is from D to A, that is donor to acceptor. This is acceptor. D to A means donor to the acceptor. So this coordinate covalent bond or day-2 bond also considered as a covalent bond, but in this bond formation, to get the bond, this type of covalent bond or the day-2 bond, that electron pair denoted or electron pair donated by any one atom present in a molecule. This concept was explained by one of the most important scientists, that is Sedgwick's. Later it was developed by Longmire scientists. Introduced and developed by these two people. This is also called a electronic theory. So the electronic theory, this electronic theory means particularly in coordination compounds. In coordination compounds, these coordination compounds also called a complex compounds. In such compounds, almost all the compounds containing such a day-2 bond or the coordinate covalent bond. So here this electronic theory, why it is called electronic means to get a bond between two atom of elements, that electron pair denoted by any one of the atom present in a molecule. For example, so here AB is a molecule. In this AB molecule, A atom containing one extra lone pair which is ready to donate electron pair to the B atom for B atom to get the octet electronic configuration. Yeah, to accept the pair of electrons from A to B, B atom contains compulsory at least one vacant orbital. Then only your B atom of an element accept a pair of electrons from A and it forms a coordinate covalent bond that is denoted by an arrow that is from a donor to the acceptor. Now this is the donor atom. Now this is the vacant orbital that is acceptor accepting atom. On the basis of the simple concepts, in first year, equilibrium acid-base theories are there. Arrhenius acid-base theory, Lewis acid-base theory, Bronsted-Lowry acid-base theory. According to Lewis acid-base theory, electron pair donor is called a Lewis base. Lewis base. Electron pair acceptor is called a Lewis acid. So according to the Lewis acid base theory, electron pair donor is a Lewis base and electron pair acceptor is called a Lewis acid. Electron pair donor is nothing but excess amount of electrons are present. This is considered as a nucleophile. This nucleophile also considered as a ligand concept. Ligand or the ligand. In second year, coordination compounds will get into this concept of ligands. Now here the B is the electron deficient species. That's why it accepts to get the octet electronic configuration. That is considered as an electrophile. It is. Now that electrophile means electron deficient species are there. Such a electron deficient species are ready to receive the electron pairs from other group of atoms to get the octet electronic configuration. Based on this simple explanation, I'll give a very simple example for day 2 or the coordination compounds. Very simple example. In first year, in Lewis acid base theory, in equilibrium concepts, your hydronium ion is there here. One example it is hydronium ion. This hydronium ion also called a hydrated hydrogen ion. This hydrated hydrogen ion formula is H3O plus. It is actually that plus is not on oxygen, that is on hydrogen atom. Here in this hydronium ion, your H2O molecule and your H plus ion, it is a proton. Originally, Iodosine atomic number is 1s1, electronic configuration is 1s1. Now its electronic configuration 1s1, it contains one electron. This is the Iodosine atom. From Iodosine atom, if it removes one electron, it becomes 1s0. That is H plus. It is a proton. Now your vacant orbital is there. That's why here the proton is ready to receive the electrons from other group of atoms. In water molecule, oxygen, the central atom of element, atomic number is 8. Electronic configuration is 1s2, 2s2, 2p4. In its outermost orbit, 6 valence electrons are there. Now here, out of 6, 2 electron pairs are there here in 2s and 2p. Out of these 2 electron pairs, any one electron pair readily donated to the proton, it forms a coordinate covalent bond. Now here the 2 hydrogen atoms are bonded with this, it forms a 2 covalent bonds like oxygen. Here are 2 hydrogen atoms bonded with 1 oxygen atom, it forms 2 sigma bonds and it contains 2 lone pair. These lone pair, either these or this, anyone at a time donate only 1 electron pair to the your hydrogen ion proton, it forms a coordinate covalent bond. It is the hydrogen ion. Now it becomes your H3 because 1, 2, 3 your hydrogen. That's why your H3O plus hydronium ion. Coordinate covalent bond. Like one of the most important example, ammonia and boron trifluorides. So the boron trifluoride are contained on vacant orbital. Now the nitrogen and ammonia contain one extra lone pair which is ready to donate. It forms a coordinate covalent. Yeah, atomic number is 5. Electronic configuration 1s2, 2s2, 2p1. Yeah, 2 vacant orbitals are there. But in excited state, its electronic configuration 2s1, 2p2. Yeah, 3 valence electrons are there. These 3 are bonded with 3 fluoride atom. 1 is vacant orbital, which is ready to receive. Here, nitrogen atomic number is 7. On the basis of electronic configuration, nitrogen contain one lone pair, remaining 3 are bond pairs. This lone pair is ready to donate to this boron to get the octet electronic configuration. Not only these simple examples, all covalent compounds, all day 2 compounds, complex compounds, are those compounds containing such a day 2 bond. All the compounds are called a covalent or the day 2 compounds or complex compounds. In second year, in coordination compounds, complex compounds, one example is there, that is CuNH3 taken 4 power plus 2. This is tetraamino copper 2 complex ion. It is a cationic complex. Around copper, yeah, the 4 vacant orbitals are there. These 4 vacant orbitals are ready to receive 1 electron pair from each ammonia molecule. That's why the 4 vacant orbitals are there. That's why 4 ammonia molecules required. That's why the 4 NH3 molecules are ready to donate. And here also pair of electrons ready to donate. Your nitrogen is ready to donate electron pairs to this. Now around the copper, your 4 vacant orbitals are there. These 4 vacant orbitals are ready to receive to get the stable electronic configuration to stabilize the molecule. That is EAN concept is there, effective atomic number concept in second year. Now this is the electron pair donor. That's why it is a LB, Lewis base. It is electron pair acceptor. It is a Lewis acid. Now it is acts as a ligand. Ligand is a species which contain at least one lone pair which is ready to donate electron pairs to the central atom of an element. Okay, so this is the coordination compounds, coordinate bond or the day 2 bond, complex bond. Now here the day 2 or the complex bond. Those compounds containing such a bonds like day 2 bond, these are generally soluble. There's any compound like A gives to B. This compound is a complex compound. Yeah, complex compounds. Such complex compounds are generally soluble in organic solvents. Organic solvents, but insoluble in inorganic solvents. Or inorganic solvent means insoluble in generally water. Now generally, yeah, these compounds having more boiling points and melting points than covalent compounds, but here less than less BP or MP than ionic compounds. Ionic compounds. Generally, such a complex compounds are the directional bonded compounds. Directional bonded compounds. That's why these complex compounds exhibits isomerism. In second year complex compounds explain isomerism, that is structural isomerism, and here stereoisomerism explained. Yeah, in structural isomerism, some examples given like linkage isomerism, hydrated isomerism, ionization isomerism, different examples. Yeah, geometrical and optical isomerism explained. These are the some important properties, some important points about complex compounds, coordination compounds, important properties. Okay, next. Hydrosyn bond. Here after ionic bond, covalent bond, coordinate covalent bond. In covalent bond, different examples given to you, polar and non-polar covalent bonds. Here one more important type is Iodosine bond. Generally, Iodosine bond is denoted by dotted lines, denoted by dotted lines, like. But here covalent bond is denoted by solid line. That solid line is simple dash like a solid line. But whereas in Iodosine bond, that bond is denoted by dotted line. That Iodosine bond, by using the word iodosine, that weak electrostatic force of attraction. Weak electrostatic force of attraction exists between hydrogen atom and highly electronegativity fluorine, highly electronegativity next nitrogen, highly electronegativity here take oxygen and here nitrogen. So here the weak electrostatic force of attraction exists between hydrogen and highly electronegativity fluorine. That's why your hydrogen and fluorine is a one molecule between hydrogen and fluorine. There exists one solid line. That is not a hydrogen bond. That is a covalent bond. Mutual contribution, mutual sharing will get a covalent bond. Whereas another important hydrogen and fluorine covalent molecule between these molecules. Same molecule, hydrogen fluoride. Here, there exists a polar molecule. It is a partial positive and partial negative. It is also partial positive and partial negative. There exists a one weak electrostatic force of attraction, that is hydrogen. Electropositive hydrogen and electronegativity of fluorine, oxygen, and nitrogen. That is called a hydrogen bond. This is a covalent bond, Cb it is, and it is a ionic bond. Sorry, it is a hydrogen bond. That hydrogen bond is denoted by dotted lines. Same similarly, your hydrogen and oxygen. Hydrogen and oxygen, like in water molecule, these are the sigma covalent bonds. And another molecule is hydrogen and oxygen. Now there exists one bond that is called a hydrogen bond. Similarly, your hydrogen nitrogen, your around nitrogen now, 3 hydrogen atoms are there, 3 sigma covalent bonds are there. Another molecule like nitrogen and hydrogen, between two same or the different molecule, there exists a bond, that is a intermolecular hydrogen bond. That is one type of hydrogen bond. So our hydrogen bond is exist between hydrogen fluorine, hydrogen oxygen, hydrogen and nitrogen. rarely exist between hydrogen and chlorine, rarely, less proportionately exist. Even though yeah, nitrogen and chlorine both are having same electronegativity values. Your hydrogen chlorine bond is not 100% existent bond because here because of large size of Cl, even though both are having same electronegativities, it's a bond strength between hydrogen and chlorine bond strength is weakened. That's why rarely exists. So finally, here hydrogen bond is denoted by a dotted line, and its bond length is greater than compared to the sigma covalent bond. When our bond length increases, bond strength decreases. So covalent bond strength is more than compared to the hydrogen bond strength. That's why there exists a bond length and energies variation 5 to 10 calories, 5 to 10 values, their kilocalories or the kilojoules values varies in their energies between covalent and hydrogen bonds. Here, hydrogen bond is a weak electrostatic force of attraction exists between like these. So many examples are there here. Based on their type of molecule, here we can again divide into two different types of hydrogen bonds. There are intramolecular and intermolecular hydrogen bonds. Now here intra and intermolecular hydrogen bonds, two important bonds are there. Your intramolecular hydrogen bond is a type of hydrogen bond which is exists between which is present within the molecule between hydrogen atom and highly electronegativity fluorine, oxygen or nitrogen. Here are types of hydrogen bonds. In this hydrogen bond, one is intramolecular HB hydrogen bond. Another one is INT or intermolecular hydrogen bond, HB. This is generally this is one type of hydrogen bond. It is also one type of hydrogen bond. Here it is present within the molecule. Within the molecule exists. Here between it exists between two same or different molecules. Same or the different molecule it exists. Generally, in organic chemistry, in aromatic molecules, at ortho position presented molecules which are linked with hydrogen, fluorine, hydrogen, nitrogen, and hydrogen, oxygen, there exists this type of bond. I'll take one example, Ortho Nitrophenol. This Ortho Nitrophenol is the best example. Orthobenzoic acid or salicylic acid or some ortho related compounds generally shows intramolecular hydrogen bond. Now ortho nitrophenol means we know this is benzene. To the benzene at one position bond OH is their phenol. Next immediate adjacent position is called ortho position. Now there exists a one bond that nitro bond is present like this. This is a ortho nitrophenol. In these two important groups between phenol of hydrogen atom and nitro group of oxygen, there exists a dotted line bond that is called a INT or a intramolecular hydrogen bond. Whereas in this case, I'll take paranitrophenol. This is P-nitrophenol. In this paranitrophenol, Your example is this is the benzene, your OH, and at para position NO2 group is present. I'll take like this. This is one example for para-nitro means intermolecular Iodosine bonding. One more example I'll take. This is double bond O and coordinate bond nitro group, which is connected with benzene, that is connected with phenol OH group. Now this is the one molecule of Ortho Nitrophenol. This is the another molecule of Ortho Nitrophenol. These two are the same molecules, like same molecules. Now one molecule orthonitrophenol OH group is connected with another orthonitrophenol oxygen of nitro group connected with the dotted line, that is between the same or the different. Such type of bonds are called a INTR, intermolecular Iodosine bonds. Generally, this intramolecular Iodosine bond strength is weaker. Its strength is weaker. It is a stronger bond. It is. That's why easily volatile. Orthonitrophenol is easily volatile compound, but these are not easily volatile. So these are not easily volatile means generally having less BP, less boiling point. Now these are generally having more BP, more boiling points. So like in organic chemistry, on the basis of inter and intramolecular Iodosine bonds, variety questions are there. Tomorrow I'll discuss about associative liquids. What type of liquids are called associative? What type of liquids are called normal liquids, unassociated liquids? Tomorrow I will discuss about these some important applications of this, and type of number of Iodosine bonds present in a water molecule and ice with the help of Iodosine bonding. Then finally 10-15 minutes, within 10-15 minutes I'll cover the last concept, very important. Guarantee one question we can expect for 4 marks, that is MOT, molecular orbital theory. Okay, read well, take care.